So we did a warm-up with exponents, and we're going to learn about logarithms and how these two concepts are related today, exponents and logarithms. So for some of you, brand new word even. So first thing we have to talk about are inverse functions. And we looked a little bit at inverse functions when we looked at like the sine of theta equals some number, or the angle whose sine is x is an angle. Remember, these are inverse functions. What is an inverse function? It just reverses inputs and outputs. So we've seen that with the trig functions. But what if you just have an ordinary linear function here? So y equals 2x plus 3, or f of x equals 2x plus 3. I put some ordered pairs in, a little t-table with an x and a y. How would I create the inverse of it? I just swapped the columns. Now what was in the y column is now in the x column. Now what was in the x column is now the y. So we're just like swapping this. And that's the inverse of it. It's the opposite. Now the question is, how can I write an expression that describes this function? And the basic technique for this is you start with the original function. And I'm putting in a y instead of f of x here. Because what we're going to do is we're going to swap the x and the y. Because I want to undo this. This says multiply an x by 2 and add 3. So I want to undo that by subtracting 3 and dividing by 2. So swap these two things. The x and the y switch positions, and then I solve it for y. So let's see. 2y is x minus 3 by subtracting 3 from both sides, and then divide both sides by 2. So y equals x minus 3 over 2. This is the inverse of that. We can also write that as f inverse of x equals x minus 3 over 2. And here's that little minus 1 like we saw with the inverse trig functions. Same kind of thing. So now if you put negative 1 in your inverse, negative 1 minus 3, that's negative 4. Divide by 2, there's negative 2. So I'm kind of reversing what we're working on here. That's an inverse function. Yeah? Okay. So what? Logarithms are inverses of exponential functions. Now we haven't even looked at an exponential function. An exponential function is of the form f of x equals a to the x power, where that a is just a constant. So an example would be f of x equals 2 to the x, or f of x equals 10 to the x. These are all exponential functions. And logarithmic functions are inverses. We're switching. So if you have y equals a to the x, or y equals 2 to the x, if you want to put a number in, how do you switch these things around? You switch the x, you switch the y, and now I want to solve it for y. Well, how do you solve that for y? I don't know, right? We don't know how to do that. So this is where logs come into play. They're the undoing of an exponential expression like this, or equation like this. So how does it work? X equals a to the y is the same as saying y equals this word log. I put a little a here and x. Now it might make slightly more sense if we say log base a of x. And isn't this the base of the power? So that's the base. And so this part here is the exponent. And this is kind of, the x that you get, but now it's over here. It's an input instead of an output. Wow. So what's here? So some examples of that. So if I have 6 to the third power is 216, how can I write this as a log? Well, the 3 is the thing that's kind of your equal to. Log base 6 of 216. So the base 6 is the same base 6. You apply that base 6, log base 6 to 216, you get the exponent. Because can you see here how 6 to the third power is 216? It says 6 to what power is 216? That's basically what log is saying. 6 to what power is 216? 3. Now this one is, I'm starting with a log. How do I turn it back into an exponent form? Well, here's my base. Log base 5 of 25 is 2. So there's the base. The exponent, which was the output, now kind of becomes input. And this input now becomes an output. So we're inverting how we look at these two different things. Do we sort of maybe see it? Maybe. We can do another example. 3 to the 4th power is what? I believe it's 81. Is that right? Yeah, 3 times 3 times 3 times 3. So how can I write as kind of as a log expression or a log equation? Well, this now is, instead of an input, it's kind of the output. And log base, what's the base? 3. And so that goes like a little subscript of 81. Log base 3 of 81 basically says 3 to the what power is 81? 4. Okay? Takes a little getting used to. Takes a little bit of getting used to. And then if I have something written like this, okay, log 2 of 32 is 5. Because 2 to the 5th power is 32. 2 to the what power is 32? 5. So it's another way of kind of expressing these little exponents, except I have different inputs as before, different inputs and outputs. The graph of them, so y equals b to the x. So any y equals a constant to the x kind of looks like this. Depending on your basis, sometimes it's a little thinner or a little fatter. Y equals x is here. And this is what a log looks like, a log function. They are symmetric around the line y equals x, inverse functions. They will work with the transformations. Remember all those transformations we did? So if I took this, let's say I had y, this was y equals 2 to the x, let's pretend, and I added 4, what would happen to this curve up here? It would move up 4. And then what if I took this thing and said minus 7? It goes, no, this is that you take the whole thing and subtract 7, the whole function moves down to 7, just moves down. If you want to move left and right, that's when you mess with this. So if I take y equals 2 to the x minus 3, what's that going to do to this? It'll move it right 3 units. And if I take this one, y equals log base 3 of x minus 7, if I'm doing that, it'll go right 7. If I put a plus, it'll go left 7. So all those same kinds of transformations that we used apply here. This is just a new kind of parent function. So just applying some of the stuff we learned if you ever need to graph those things, which someday you will. All right, so let's go again, a little more practice with this. So log base b of y is x means the same thing as b to the x equals y. So let's see now. For this first one, can we write this as a log equation? So one way to start is, remember, it's going to be log base something. Well, I know what the base is, right? What's the base? 5. So a little subscript for 5. Log base 5 of what now? 125. The thing that was the output is now the input, and it's going to equal 3. The thing that was the input is now the output. 5 to the 3rd power is 125. It answers the question, 5 to what power is 125? 10 to the 5th is 10,000. I want to write this as a log. So log base what?
10.
10, because here's base 10, right here. Of what? Of 10,000. So the thing that was the output is now the input, and that equals 5. 10 to what power is 10,000? 5. Questions on this part here. It's going to take maybe a little practice with it. But you kind of see where little pieces go. Okay. Now this one, I'm starting with the log, and I want to express it now with an exponent. So what's my base? 2, right here. And Rohit, what power am I going to raise it to? 3 equals 8. 2 to the 3rd power is 8. On your paper here, there's 2 log 4s for some reason. Just erase one of them. Just cross it out. This one should just be log base 4 of 1 equals 0. So how can I write this as an exponent? Jerry, how do I write that as an exponent?
4 to the power of 0.
Exactly. Right? This says, here's your base, to this power equals this. Now we've got fractions. Whoa! Rohit, what's happening here?
1 to 4.
1 4.
1 4.
To what power?
-1.
Yeah.
4.
And doesn't? Is this a true statement? Why? What does this mean, this -1? Yeah, what's that mean? Jerry, tell me about this.
It's raised to the power of -1 to the first.
Well, this means this whole thing, let's say it was in a numerator, now it's in a denominator. That's one way to think about it. And then how do you simplify this thing? Anybody know how you simplify something like that? You can multiply top and bottom by 4, right? Cancels this out, you get 4. That works. The other way to think about it is you can say, well, can't the -1 apply to the top and the bottom? Right? Isn't that one of our exponent rules? What is 1 to the minus? Well, this says I'd rather be here, and this one says I'd rather be here. You're back at 4 again. So it works. So you can have bases that are fractions. That's allowed. You can do that. What do you think, you guys? Yeah?
Yeah.
Yeah? Uh-huh. We say uh-huh. Okay. We're going to think about some other things here. And if you think you know, raise your hand rather than shouting out. I'm not telling you what the base is, and I'm not telling you what b's value is, but can we make a conclusion? If your base and this number here are the same, so log base 3 of 3, log base 10 of 10, log base 100 of 100, what do you get? And think about what this means. B to what power is B? Raise your hand if you think you know. So far, one person. See how long we get? Who's thinking? Who's thinking? Think about it. B to what power is B? 4 to what power is 4? 10 to what power is 10? Thomas, what do you think? 1. B to the 1 power is B, right? So whenever these values are the same, that's the same as 1. Okay, same way as thinking about that. B is here, so I'm not telling you what the base is, but this number here is a 1. So B to some power is 1. If you think you know, raise your hand. B to some power is 1. What do you think, Rohit? Well, B to B? Close, he's thinking about. Think about it a little bit more there. What do you think, Krishna? 0? B to 0, 1. Anything to the 0 power, 1. So whenever you take the log of 1, no matter what the base, always going to be 0. Good thing to know. It is. So let's kind of look at some more examples to kind of evaluate these logarithms. Log base 10 of 1,000. So you're thinking 10 to what power is 1,000? And I'm looking for people who have not raised their hands yet. Make sure we know. And I'll call in if you want. So you might as well think of one that you think you can get and raise your hand for it. 10 to what power is 1,000? Rachel? 10 to 100? So 10 to 100 means 10 times 10 times 10 times 10 times 10 times 10. That's going to be more than 1,000. Try again. 10 to the 10 to the 10? That's going to be 10 times 10 times 10 times 10 times 10. Try it again. 10 times how many times gets me to 1,000? 10? Not 10 times 10, right? Because that's 100. 10 times 10 times 10. Does that work? That's 3. So 10 to the 3rd power, because 10 times 10 times 10 is 1,000. Let's see if we can figure out this one. 4 to what power is 64? Jerry. 3. 4 times 4 times 4 is 64. Well, look what's happening here. Log base 5 of 1/5. 5 to what power is 1/5? Yes, sir. -1. Let's think about that. 5 to the -1. Is that 1/5? Yes. Nice. All right, let's see here. Log 1/5, base 1/5 of 125. What do you think, Dick? -5? Oh, come on, you're in right track.
If it was
Right
-5,
track, it
then
would be a
it
bigger
would
number.
be 1/5,
-3. 5 to the 3rd power is 125. But I'm making it negative. That says take this 1/5 and raise it to the -3rd power. Right? So flip everything up. 5 to the 3rd power. Whoa! This one easier. So I should see more hands. Now that we've got some hard ones, log base 6 of 36. Same. 2. 6 to what power is 36? So do we see what's happening here? A little bit better, maybe. What's the question? Ask. We have no questions. Okay. We have no questions. That means we're ready for the next big thing. which is the properties of logarithms. We did this in the warm-up. We're going to do it again. The laws of exponents. X to the n times x to the n.
I thought the next big thing was the new Samsung Galaxy.
No, oh no, this is better than the new Samsung Galaxy. It's better than all that stuff. Way better. You tell me, Christian, x to the m times x to the n is what? Get your mind, get it back there, Rowan, help me out.
It's, the n.
M plus n, right? If you have the same base for adding the exponents, it says you have m factors of x times n factors of x more. There are m plus n factors of x. Now how about there's m factors of x along the top and n factors of x along the bottom? You ready to try again, Christian?
You subtract the
Right. So this one, x to the m minus n. What about a power to a power? Yeah, right there. Yes, and that's the case where you multiply them. Okay, so we want to remember that because with logarithms, because it's inverse, you're going to see a similar kind of idea. Similar, but not very similar. Okay, so these are the properties of logarithms. We have a product property, we have a quotient property, we have a power property. The power property, for some reason, is repeated twice. You can cross one of them away. It should look like this. Log base b of m to the n equals n times log base b of m. I don't know why it's there twice. So erase whatever, cross it out. Product property states, if you have a log with a certain base of a product, you can split apart the product. Log base n, log base b of m plus log base b of n. If you're taking the log of a quotient, then that's a subtraction. Log base b of m minus the log base b of n. And if you have a power in there, the power should go in front. So log base b of m to the n power is n times log base b of m. So we're going to look at some examples here. Now there's a little note. Notice there's no base mentioned. It just says log 6xy. When it doesn't say anything, that's you assume a base of 10. It's kind of like when you see a square root, right? We know to assume a 2. There's nothing there. So if there's nothing here, assume a 10. Yes, sir.
Also, these are different.
I'm looking at what are you looking at here?
This needs to multiply to the 12th, this one to the 8th first.
Oh, that's a good question. I think you're right. Okay, so this says, since I'm multiplying a bunch of stuff, that's the same as the log of 6 plus the log of x plus the log of y. We call this expanding a logarithm. This is an expansion. If you have log of x over 7, then the quotient property comes into play. That's the log of x minus the log of 7. And this last example, bottom of page 2, log of b to the a power. The a can come out front, and that's a times log b. These are examples of expanding, and I could just think of another one real. I'm trying to think of one. Oh, not yet. How about thinking about condensing? We can go the other way. And this is, I'm just adding this so you can stay on page 2. So if I had something that said the log of a plus the log of b plus the log of c, and I put them into one log, what would it be? Right, the log of a times b times c. So you can go both directions. And they can get a little bit more complicated. Let's look at it again. I'm just thinking of some here. Suppose now I'm going to go back to expansion. If I had the log of x squared over y to the third power, y cubed, how do you expand something like this? So it's 2 steps. The first thing I'm looking at is it's a quotient. So that's the log of x squared minus the log of y cubed, right? So far so good?
Yeah.
And then now I've got a power, so that means I can put the 2 in front. Minus 3 log y. So we can combine this. And then if you're given like this one, say, hey, put it back. You have to remember that if there's a 3 in front, put it back and work backwards. Sometimes you want to expand, sometimes you want to condense. It all depends on what you're doing with these things. But you're not going to really know But it's helpful stuff. Was there a question? What is that question? We're all fine? You still here? Okay, you're still here. Good. Because this is one of my favorite things that I get to teach. I'm so excited. Euler's number E. If you look at my backboard there, on the top left, you see Neil deGrasse Tyson? See that guy? So right next to him to the right is Leonard Euler. And he is, or was, a Swiss mathematician. And he did a lot of amazing, amazing things. One of the things he did was kind of come up with Euler's number. It's E, not because it's Euler. He had different numbers. He had A, he had B, he had C, right? He was working on different numbers. And he stopped at 8 because this is a really cool number. So kind of like pi, it is irrational. It kind of goes forever there, no pattern, 2.718, blah, 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 blah. And it turns out that this number, this wacky number, is found in nature. It's for exponential growth and decay. For instance, finding compound interest uses E. So compound interest in a bank. Radioactive decay uses E. This number appears, and it's like really cool. I don't know how we figured this out, but I'm glad we did. Helps us out. So we very often will look at this particular exponential function, y equals e to the x. And because it's exponential, I can look at its inverse as well. So I would switch them, right? I would say x equals e to the y. So y equals log base e of x. And we found in math, we tend to use log base e a lot. So instead of having to write log base e, we can't just get rid of the e because that's log base 10. That's the default. So we created a new kind of way of saying log base e, and that's where this ln comes in. So I don't know if you ever noticed it on your calculator. You see this like log button here? Look underneath it. There's an ln button. That's it. It's so important. It's right big button on your calculator. So when you see an ln, it's just log base e. I believe yln. I'm told because he was Swiss and he lived in the French part of Switzerland and he spoke French that, who speaks French? Anybody speaking French? Logarithme naturel, something like that. ln, so that's they put the adjective at the end, logarithme naturel, but it's natural log is what it stands for. Natural log, that's what we call base e. So when you see ln x, we're talking about natural logs, and they look the same, it's just a different base, a number between 2 and 3, so that's what it looks like. So we use this thing all the time. So I want you to get used to seeing it. I know in like calculus stuff we almost never saw log, we always used ln. So let's look at some more examples here. We're going to be expanding and we're going to be condensing a little bit here. This one I think is all, both. Okay, so log of 2xy, this is log base 10 because there is no number there, and actually all these examples are either log base 10 or natural log. It works for any log. You could have put a 5 here, the rules all apply no matter what base you're using. So how do I expand this guy? Jerry?
Log 2 equals log x plus log y.
Right. Because it's a product, you're just going to take the log of all of them and add them. So log 2xy equals log 2 plus log x plus log y. How about B? Now I've got the natural logs, the ln of 4 over x. ln 4 over x. Christian, what's back in B?
Natural log 4 minus natural log x.
Okay. Now how do we say these? It's not really correct. What you said is correct. That is natural log 4 minus natural log x. We tend to say either ln 4 minus ln x, or, real quick, and just too much trouble, you can say ln 4 minus ln x. That's okay too. I've heard that used. Yeah. All right, this one I want to expand that. And I've got a property, right? Power property. So what's this going to be? X log y. Simple as that. And so that illustrates, the top 3 ones. Fairly straightforward. Now they're slightly less straightforward. This one a little bit more complicated. So let's see. You're going to break them down, and especially at first, you're going to want to do this in steps. So the first thing, we have a quotient. So we're going to do a subtraction. So it's the ln of 5x cubed minus the ln of y. That takes care of the quotient part of it. Now in here I see a product. So that's ln 5 plus ln x to the 3rd power minus ln y. That's expanding that. And I got one more thing I can do here. I've got a power. So this is going to be ln 5 whoops, plus 3 ln x minus ln y. Wow. You know, why do you do this stuff? It helps you sometimes simplify. There are reasons why this will come in handy. Not here, at the moment. So there's lots of different things. The more you do with this, the quicker you start seeing how this works. Now this one is an expansion, but I want to condense this one back. So I want to put it back like smaller. So let me see here. I can't help it. My mind immediately sees this thing in front and wants to put it back. So again, we're going to do this in steps. So I've got ln 9 plus ln 2 to the third power minus ln 3. Now here's a plus of 2 of these logs. So I can condense them back to the product of 9 times 2 to the third power. So minus this, right, ln 3. A minus is a quotient. So this becomes the ln, this would be my numerator. 9 times 2 to the third power over 3. Notice there's only one log, and this is now one expression. Don't put log and log here. It's not in both places, it's here. Now that we can simplify this number, well, that becomes, right, a 3, and that becomes a 3. 2 to the third is, what, 8? And 8 times 3 is 24. So that's the ln 24. And these have values. You can just put that in your calculator. Say, gee, what is the natural log of 24? Well, let's find out. 24. And it's approximately a number, 3.178. So, like, these are actual numbers. I forgot what it was already. I think it's 7. Yes, okay, 178. Memory. So, yeah. This guy here, let's see what's happening. I'm working backwards. So I want to put the 3 back up as a quotient. I'm sorry, as an exponent. X to the third. I'm adding these things. So it becomes the natural log of 4x to the third power. If you want, you can do this. If you want to just make sure it's, you know, it's all kind of grouped together. But it's okay. If you did, that's okay. And let's see what's happening here. Oh, this one they want me to expand it. ln 4 minus ln 7. So you get after a lot of practice, now a lot, you start being able to go back and forth with these things. Questions? You're just fine. Absolutely. You okay? Okay. All right. Because you know what comes next are these U-tries. I will say this. So for this first one, what are we doing with this one? You're expanding it. This one looks like you're condensing it, and the other one as well. This looks like we're condensing it into one thing. These are think problems, so I'm going to give you a chance to kind of work on that and think about these guys. All right, let's see what happened here. So how we do like A? So it's log 7, right, plus log x squared. But log x squared is 2 log x. Did we get this guy at least? Yeah. Questions on A. That one's a little bit, just a little bit of complication. Question on A.
Log 7 plus log x plus log x.
Well, that's how you start. No, it's log 7 plus log x squared, right? But then you say I've got the power rule, so I can put the 2 up front. And that's where this comes from. So you didn't quite get there all the way if you didn't put the 2 up front. This guy here, there's a bunch of stuff to do. So let's see. First of all, that 4 in front of the y, let's put it back up here. And now I've got this log of this product here, xy to the 4th. Yeah? Minus 5 log z. Well, I can put that back. That's log z to the 5th. Now it's a subtraction, so that's a division. That's a log of xy to the 4th over z to the 5th. Now I'm seeing some people are putting log here and log here. There's one log. It's not the same thing to say the log of xy 4th over log of 25. That's not the same thing as log of this whole expression. So be careful. There's one word log. This guy, word from the inside out. So what does that mean? Well, let's see. This 4 is in front of this ln A, so I'm going to put that back over here. So now I've got 2 times ln of a to the fourth times b minus, now I'm putting the 4 back up here, right? So let's see, what's going here? I've got a 2 in front of what? ln of a to the fourth b over c to the fourth. Now what does this 2 in front mean? It means I can put it back as this thing squared. Ah, as this is that. If you got C, you get this.
Yeah.
If you're still a little struggling, that's okay, perfectly normal, it's a hard one. Yes? That's fine, just leave it like this.
What happens if you do?
Nothing. But you can leave it like this. If you said, what'd you say? Make sure you squared them right. What'd you say? A to the 8th, b squared, c to the 8th. That would be if you expand that square out. All right, now this one here, I don't know if anybody tried it. Get rid of this thing here. What was I talking about? What I wanted you to do is I wanted you to apply all these properties and see what you get. So this one says, okay, here's an exponent, so it goes in front, right? In front of what? The ln of 1/4, which is a subtraction. That's the ln of 1 minus the ln of 4, right? I just kind of undid this one. Now what is the log of 1, no matter what the base? What's the log of 1? 0, because anything to the 0 power is 1. So I've got negative 1, 0 minus ln 4. And 0 minus ln 4 is just negative ln 4. And a negative negative is a positive. So I got back to ln 4. That's all I was trying to see if you could kind of work way back. That's how I showed that ln 4 and this are the same thing. This one now, like solving an equation, like really? Well, what can we do here? Log base 3 of x. This is both 3, right? So that means I could use that product property. That's really the same as log 3 of 4 times 7, right? Which is the same as log base 3 of 28. So let's match up this. Log base 3 of x is the same as log base 3 of 28. So what's x? 28. So these little log properties can help us solve equations as well.
Why?
What? Question? Yes, Rohit. Are we doing proofs with these? You know, this kind of thing here, this justification is the kind of proof that you're going to see in upper math. It's like you justify each step. So it's kind of like one. So yeah, you do a lot of that kind of thing, proving something is identical to something else as you move up the chain. If anybody's going to trig next year? Anybody? Because you'll be doing a lot of this kind of stuff when you get into trigonometry. You prove things are identical to something else in this kind of manner. Doing a lot of that. And then let's see, what should we do? I don't know how to start this now. I guess I'll have to, because we're here, right? The last thing I want to talk about is this change of base formula. Now we have a few minutes so we can do this. Shush. All right, change of base formula. If you look at your calculator, we have log. You see the log button? So what base is that? 10. We have an ln button. What base is that? E. What if I need something log base 6? Not going to help me, right? Hidden in the calculator, buried, there is another way to do this. However, not all of them. I don't know if it's on this one. Some of the later calculators buried in there's another function. But we don't care. We don't need another function. This is a way to kind of convert bases into things that we know. So what does this say? So let's say you have log base c of some expression here. It is equivalent to log base a over log a over log c of another base. Log a, log c of a different base. So we know two bases that are on our calculator. We have log base 10, that's this one, and we have log base e, that's this one. So if I want to know what log base 5 of, I'll pick a number, 23 is, I can say it's either log base 10 of 23 over log base 10 of 5, or I can use the natural log. Do you mean to tell me this and this are the same thing? Well, let's let's see. Whoa, where'd it go? Come back. Is this the same as that? Well, okay, clear this guy. So if I take the log base 10 of 23, and I'm making up these numbers, so I should hope they're not crazy numbers here, over log 5, I get that. Now let's try it with natural log in both places. Natural log 23 over ln 5. Yep. And it is log base 5 of 23. That's what that is. So this is a way of working with other bases besides base 10 and base 8. Okay. Helpful in converting a log to another base, especially with our calculator. So some of the later ones, there's another way, but don't do that. So let's look at this example. Log base 3 of 8. Now you can't do that in your head, can you? 3 to the what power is 8? I don't know, right? It's not an integer. So you can either do log base 10 of 8 over log base 10 of 3, or you can do natural log of 8 over natural log 3. I will say I tend to do this just because, I don't know, when you get a diagram, you use this one more than that one, but either one's correct. So let's see, what is that? It's going to be log 8 over log 3, and it's approximately 1.893. How about that? That's log base 3 of 8. So if you raise 3 to that power, you get 8. Log base 2 of 15 over 2. Okay, so you take the log of the thing you're trying to find over the log of that base. So I'm using natural log. You can use log base 10. So wait a second. Look, I can make this 15 minus root 7, can't I? And this harkens back to the day that we did not really know how to do this. Before calculators, right? Dinosaurs were roaming the earth. We used to have like log tables, and they didn't have like every fraction known to man on there, so you had to kind of pull them apart. So if you want to be old-fashioned, you can try this, or you can actually take our calculator lets us do this. Why does somebody, you do this, and I'll do this, and let's see if we get the same answer, okay? But let's have a little fun. Okay, so this is 10, 15. Minus 7. And then I'm going to divide by 2. And do we get the same thing?
Yes.
About 1.09, 1.1-ish? Or something like that, right? So you can do it either way. Either way. This is for old people like me. And now we are good. The you tries are when you come back. Okay, so we learned this change of base formula, which is, just to repeat it, you take the log of the thing you want the log of over the log of the base. And we can use base 10 log, or you can use base e log. So I think we have some u tries over here. So give these two a try. Figure out what the log base 5 of 12 is. So I want to see the little fraction you're setting up, and then come out with a number. Your answer should be a number to the nearest thousands. Let's do that. To the nearest 1,000, meaning, write 3 decimal places. See if you can come up with that. For these guys, hopefully it won't take too long. Just going to pop up the answers if you want to check your work. Question?
When it says given b is greater than 0, b is not equal to 1, why can't we just say b is greater than 1?
Don't look funny here anyway, but you can't, yes. We're not looking ahead though. This is where we're stopping today after this. So we can talk about that other thing. Are we getting this and this, or are we still stuck? Basically, all you do is you say, I used natural log. You might have used log base 10. Put that in your calculator. You should get this. This one, maybe use log. Doesn't matter. Either way. But you can say log of a fraction. Or, if you got really fancy, you did this, and you said log 3, right, minus log 4. These are equivalent. You get the same thing, but you should get this. So how'd this go? Did we get that, or do we have questions on converting logs with different bases? Anything? Nothing? Okay, this is our our stopping point. We will do a little bit more. That's the remainder of these notes next time. End of part one.